When each of these switches powers up, or when Cisco switches power up, they immediately start sending out frames to each other out of all ports called BPDUs, or Bridge Protocol Data Units. Now, these BPDUs have 4 fields in them that are of importance to us as CCNA candidates. These fields are root bridge ID, root path cost, sender bridge ID, and sender port ID. These fields I will explain as we go along through the spanning tree process, but if you notice, these fields are quite similar to the spanning tree decision process, the only pretty much difference being that the word lowest is in front. Now, before I move on, I have to explain what a bridge ID actually is. A bridge ID for a switch is a combination of a priority field plus your MAC address. So your MAC address is 48 bits, and your priority is 16 bits. 16 to the power 2, so 16 to the power 2 is 65,536. Okay? The priority field can range between 0 and 65,535, which 0 inclusive makes 65,536. The priority field for each Cisco device, each Cisco switch, is set to 32768. So every switch has a bridge ID with the priority field set to 32768. How did they come up with 32768? Simple, 65,536 divided by 2, smack in the middle. A root bridge is elected according to the lowest bridge ID. So the switch with the lowest bridge ID becomes root. So now if every switch's priority field is set to 32768, and that is same, the switch as a tiebreaker with the lowest MAC address becomes the root. So now, as I said previously, that when each switch powers up, they start sending BPDUs to each other every 2 seconds. Now, each switch initially announces that it's the root. It announces itself as the root by setting the root bridge ID field in the BPDU equal to the sender bridge ID field. So each switch is basically saying the root bridge, for example, switch A is saying the root bridge is AAAA and I am AAAA. Hence, I am the root. Now, when a switch receives a BPDU from another switch with a lower bridge ID or a better bridge ID, in spanning tree, a lower number is always better. So when a switch receives a BPDU from another switch with a lower bridge ID, it stops sending its own BPDUs and starts relaying those superior BPDUs. Given enough time, the switch with the lowest bridge ID, or in this case, since the bridge ID field is priority and MAC address, and the priority field is set to 32768 for all switches, the switch with the lowest MAC address becomes the root bridge. So all other switches in a layer 2 topology will relay the root bridge's BPDUs and not produce their own BPDUs. So in this case, switch A has a MAC address of AAAA, switch 2 has a MAC address of BBBB, switch 3 has a MAC address of CCCC, and switch 4 has a MAC address of DDDD. In this case, everybody starts off announcing themselves as root bridge by sending BPDUs with the root bridge ID field equal to the sender bridge ID field. Eventually, as you see, in hex, A is a lower number, then C, then B, and then D. Eventually, in this topology, switch A will become root and continue sending BPDUs, and everybody else will be relaying the BPDUs switch 1 sends. So in the 4-step decision process, the first step is the lowest bridge ID. And using just the first step, we have elected the root bridge. So the root bridge election occurs according to the lowest bridge ID. Now, again, in this case, since the bridge ID field consists of priority and MAC address, and everybody's priority is the same, which is 32768, the tiebreaker becomes the lowest MAC address. And the switch with the lowest MAC address becomes the root bridge. In this case, switch 1 becomes the root bridge. The next step step 2 in the spanning tree convergence process, from spanning tree to go from beginning to end, that's what convergence is a root port election per non-root switch. So I'm going to erase this. The root port election only happens on non-root switches. Which one of these in our topology are non-root switches? Switch 2, switch 4, and switch 3. Switch 1 is your root bridge. Now, root port election happens according to root path cost. And what is root path cost? Well, spanning tree designates path costs. You can think of it as distance for each link speed. For link speeds of 10 megabits per second, the cost is 100. For link speeds of 100 megabits per second, the cost is 19. And for link speeds of 1000 megabits per second, the cost is 4. In our topology, if you look, all these links say F, 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 which means all these links are fast Ethernet. So the path cost for all these links is 19. Now, remember, at this point, switch 1 with MAC address AAAA is your root bridge. So switch 1 is the only one sending BPDUs. So remember this rule. The path cost inside of a BPDU, the root path cost inside of a BPDU is incremented when a BPDU enters a switch, not when it leaves the switch. Now, if you think of this cost as distance, when a BPDU leaves switch 1 port F01, the root path cost inside of that BPDU, and the root path cost is the distance or the cost from a local switch, let's say switch 4, to the root bridge. So the distance from the root to the root has to be 0, correct? The distance to yourself from yourself is 0. So a BPDU leaves switch 1, port F0/1, heading out to switch 2, and another BPDU leaves switch 1, F0/2, heading out to switch 3. Now these BPDUs, when they leave switch 1, have a cost of 0, a root path cost of 0. When this BPDU leaving switch 1, port F0/1, enters switch 2, F0/1, the cost is incremented to 19. Now, we're looking at switch 2 at this point. We're just looking from the point of view of switch 2. The other BPDU that left switch 1, F0/2, has its cost incremented to 19. 0 plus 19 is 19 at switch 3, F0/2. Now, that BPDU transverses switch 3 and leaves switch 3, F0/1, still with a cost of 19. Remember, we only increment root path cost when a BPDU enters a switch, not when it exits a switch. Then the BPDU enters switch 4, F0/1, and another 19 is added to the root path cost, since this is a fast Ethernet link, and 19 plus 19 is 38. So the cost at F0/1, switch 4, F0/1 is 38. The same BPDU leaves switch 4, F0/2, and F0/3 with a different sender port ID. So the sender port on switch 4, F0/2 is F0/2, and the sender port over here is F0/3. So it's the same BPDU, nothing else has changed except the sender port ID field inside of the BPDU. This BPDU transverses this link and enters switch 2 port F0/2 and switch 2 port F0/3, and the cost is incremented by 19 again. So 38 plus 19 is 57. 57 here and 57 over here. Switch 2 now looks at the cost, which is 19 on port F0/1, and looks at the cost at F0/2 and F0/3, which is 57, and the lowest root path cost on switch 2 is on port F0/1. Hence, F0/1 on switch 2 is elected, I'm going to erase that 19, as a root port. So I'm going to go ahead and erase these numbers because we're going to work through the rest of the switches. Now once again, let's look at switch 3. A similar process is going to happen that happened for switch 2. A BPDU leaves switch 1 F0/2 with a cost of 0, with a root path cost of 0. When it enters switch 3 F0/2, the root path cost is incremented by path cost, which is 19, and the BPDU now has a cost of 19 as it sits here on switch 3 F0/2. Now, again, another BPDU leaves switch 1 F0/1 with a cost of 0, with a root path cost of 0, and enters switch 2 F0/1, and the cost is incremented to 19. The same BPDU transverses switch 2, and the cost is not incremented when it leaves switch 2 F0/2 and F0/3. The BPDU enters switch 4 F0/2 and F0/3 with a different sender port ID, because the sender port ID from switch 2 will be F0/2 and F0/3, and the cost on that BPDU is incremented once again to 38 on port 2 and port 3 of switch 4. Then that BPDU leaves switch 4 heading up towards switch 3. It leaves switch 4 F0/1 and enters switch 3 F0/1, and the cost is incremented to 57. Switch 3 compares the cost at F0/2, which is 19, and F0/1, which is 57. Since switch 3's cost at F0/2 is lower, remember, the decision process, the second step says lowest root path cost. Switch 3 F0/2 becomes your root port. Once again, I am going to erase the cost, and then we are going to work through switch 4. Looking at switch 4 now, a BPDU leaves switch 1 port 2 F0/2 with a root path cost of 0 and enters switch 3 F0/2, and the cost is incremented by path cost, which is 19. So the cost is 19 over here. And then the BPDU transverses switch 3, leaves switch 3 F0/1, and the BPDU enters switch 4 F0/1, and the cost is incremented to 38. The other BPDU, the route sent out, left port F0/1 with a root path cost of 0 and enters switch 2 F0/1, and the cost is incremented to 19. Then this BPDU transverses switch 2, and it is converted to two separate BPDUs. It's actually the same BPDU, the only difference being that the sender port ID field inside of the BPDU now says port 2 for the BPDU leaving port 2, and port 3 for the BPDU leaving port 3. These two BPDUs enter switch 4 port 2 and port 3, and the cost for both of these is incremented to 38. At this point, switch 4 compares the cost at port 1, port 2, and port 3 and discovers that the costs are the same. So it cannot elect a root port yet. Hence, switch 4 has no other choice but to move to the third step in the spanning tree decision process, which being lowest sender bridge ID. Now, the sender bridge ID that switch 4 is receiving on port F0/1 is the bridge ID of switch 3 with the MAC address CCCC, and the priority being the same, 32768. And the bridge ID switch 4 is receiving on port 2 and port 3 is BBBB from switch 2. So the sender port ID is the ID, or the sender bridge ID is the ID of the sending switch, which is with the priority 32768 on switch 2 and MAC address BBBB. So switch 4 compares the sender bridge ID on port 2, port 3, and port 1. Since the sender bridge ID is lower, since BBBB is lower than CCCC, switch 4 now starts looking at port 2 and port 3 to elect a root port. Now, the sender bridge ID on port 2 is BBBB, is the bridge ID of switch 2. And the sender bridge ID on port 3 is also BBBB. So switch 4 now still can't decide whether port 2 or port 3 is going to be the root port. Hence, switch 4 has to move to the last step in the spanning tree decision process, which is the lowest sender port ID. So the sender port ID, which is the ID of the sending switch, on port 2 of switch 4 is 2, and the sender port ID on port 3 of switch 4 is 3. Since 2 is lower than 3, F0/2 on switch 4 becomes your root port. So at this point, we have concluded the second step in the spanning tree convergence process, which was elect a root port per non-root switch. So switch 2 has a root port, which is F0/1. Switch 4 has a root port, which is F0/2. And switch 3 has a root port, which is F0/2. The last step in the spanning tree convergence process is to elect one designated port per segment. So, as I mentioned earlier, there are 5 segments in this topology. Between switch 1 and switch 2, between switch 1 and switch 3, between switch 3 and switch 4, this link between switch 3 and switch 4, and the 2 links between switch 4 and switch 2. So 1, 2, 3, 4, 5. Now at this time, when we were electing the root port, our view of the topology was based on we were sitting on each switch and looking at how BPDUs enter our switch. Now we're going to take a view of the topology by sitting on this segment. So there are 2 ports on the segment between switch 1 and switch 2, which being switch 1 port 1 and switch 2 port 1. The designated port on each segment is also elected according to the lowest root path cost. So let's look at switch 1 first. On the segment between switch 1 and switch 2, the root path cost on switch 1 is 0. F0/1 is 0, since the distance from switch 1 to switch 1 is 0. And then the BPDU leaves F0/1 switch 1 and enters switch 2 F0/1, and the cost is incremented to 19. So between 0 and 19, 0 wins, since the lowest root path cost wins, port 1 switch 1 becomes the designated port. So I'm going to put a D on port 1 for switch 1. Now, on the segment between switch 1 and switch 3, the root path cost at switch 1 F0/2 is 0, and the root path cost at switch 3 F0/2 is 19. So between 0 at switch 1 and 19 at switch 3, switch 1 F0/2 becomes your designated port. Always remember, all ports on a root bridge will become designated port. No matter what segment, no matter who they are connected to, on every segment, the cost from the root to itself is 0. So all ports on a root bridge will become designated ports. Now let's look at the segment between switch 3 and switch 4. The cost in the BPDU, the root path cost inside of the BPDU, as it leaves switch 1 and transverses switch 3, and then leaves switch 3 F0/1 is still 19. When this BPDU enters switch 4 F0/1, the cost is incremented to 38. So 19 at switch 3 F0/1 and 38 at switch 4 F0/1. So between 19 and 38, switch 3 F0/1 becomes your designated port. Now let's look at the last 2 segments between switch 4 and switch 2 and switch 4. The root path cost at switch 2 F0/2 and F0/3 is still 19. It was 0 as the BPDU left F0/1 switch 1, the route. It got incremented to 19 at switch 2 F0/1. And when the BPDU leaves switch 2, F0/2 and F0/3, the cost is still 19. Remember, the cost is only incremented when a BPDU enters a switch. So when this BPDU travels, when these two BPDUs travel and enter switch 4, F0/2 and F0/3, the cost is incremented from 19 to 38. So the cost is 19 at F0/2 and F0/3 of switch 2, and the cost is 38 at F0/2 and F0/3 of switch 4. So F0/2 and F0/3 of switch 2 becomes designated. Now, are we done with the spanning tree convergence process? Yes, we are. Now, at this point, we got to see what happens to these ports. Are they put in blocking? Are they put in forwarding? Now, can we forward traffic? So let's get to that.